Hello everyone, welcome back to the Fundamental Econometrics course. In this meeting, we will discuss about the two-period panel data analysis, which is materials from chapter 14 of Jeffrey Wooldridge Introductory Econometrics. Let's fire away. So in this lecture, we're going to discuss several subtopics. The first one is the data structure of a panel data, particularly two-period panel data. Analysis of two periods panel data, first difference estimation, and then the last one we're going to conclude the lecture. So along the way, we will also provide a discussion in Stata to provide you with illustration of working with panel data, particularly two period panel data. So let's start with the structure of panel data and consider that we have two period panel data. So in a panel data setting, we're going to see the same units or entities over time. So it could be the same individuals in two periods. It could be the same households in two periods. It could be the same firms in two periods. So the idea is that you observe the same set of entities, not only in one period, but also in multiple periods. In this case, it's just two periods. Okay. So in the first period, what you'll see is the dependent variable of individual I in the first period. And then in the second period, you're going to observe the dependent variable Y for the same individual I in the second period. Okay. And suppose that you have X, K explanatory variables for each individual I from 1 to n. Okay. So basically you'll have a total of 2n observations of n individuals. Okay. And period 2 could be some years. It could be months, it could be weeks, it could be semester, it could be year, depending on the level of analysis. Okay. Panel data is also referred to as the longitudinal data. So if you hear panel data or longitudinal data, it's actually the same. It's actually the same term. Okay. All right. So basically, at a minimum, the statistical methods must recognize that the outcomes for a particular unit will be correlated over time. Okay. So think about observing a student's test score over the years. Okay. So you observe the student test score at the beginning of the school year, and then you also observe the test score of the same student at the end of the school year. Okay, so basically you have the t and then the t minus 1. Now, at least you have to recognize or you have to acknowledge that the student test score at the end of the year will be correlated with the student's test score in the beginning of the school year. If we take all the data from the students in a particular data set. Okay. Now, in a panel data setting, it's going to be a contrast with the pool cross sections. Why? Because if there is some overlap, we're going to ignore it. Okay. And usually we wouldn't know that there's actually an overlap. So what's the main benefit of using a panel data? So we're not going to be able to find panel data for every problems or every research questions that we're interested in. However, if we do find a panel data, what are going to be the advantages? Well, with multiple years of data, we can control for unobserved characteristics that do not change, or perhaps it changes, but at a very slow or a slow pace over time. And this is going to be very useful for policy analysis. The reason that it's very useful for policy analysis is that the effect, we can identify the effect of a particular policy on a particular outcomes. Okay. So for example, what is the effect of providing a training grant on the productivity of workers? What's the effect of enterprise zoned on, say, the unemployment claim in a particular city. So those are several research questions that we're interested in and something that we're going to work on data later on. Okay. Now, we're going to have what's called a balance panel if we observe the same time periods for each unit in the data set. Okay. Note that it's going to be easier to have a balance panel for larger units. So for example, if we observe data at the school level, or for example, if we see the data at the city level, at the district level, or at the provincial level, then it's likely that we'll get a balanced panel. However, at a disaggregated level, so for example, at the individual or at the families level, following the same units over time can be challenging. So for example, there is a famous data set or a famous longitudinal data set referred to as the Indonesian Family Life Survey, or the IFLS. A lot of our students actually utilize the Indonesian Family Life Survey for their undergraduate thesis. Now, it's interesting that the Indonesian Family Life Survey acknowledges individual unit as well as the household unit. Now, one of the challenges in using the IFLS is that there are attritions over time. So for example, in one particular wave, you're going to observe an individual or a household. However, in the next wave, there's a probability that the individual or the household is not going to be observed for many different reasons. Okay, for example, the individual can pass away, or the individual refused to be interviewed in the next set of the survey, or for example, they were interviewed, however, they were not finished, and so they do not want to continue. So there are several different reasons why there could be attrition. Okay, and so just given the backdrop of the benefits of the panel data, we're going to dig deeper into the analysis of two periods of panel data. So we'll start with a very basic case of two-period panel data with just T1 and then T2. Okay, so T1 and T2 doesn't have to be 1 month apart. It doesn't have to be 1 year apart. It doesn't have to be 1 semester apart. You can actually have two-period data set that is 2 years apart or 3 years apart. And in the case that we're going to discuss in data, the data set is actually 5 years apart. But it still holds that you observe the same set unit in T and then T plus 5. So basically you still have 2 periods. Okay, and then hopefully we're going to have many cross-sectional observations, which is I equals to 1 to n. Now, basically, when we observe the data, we will definitely observe the outcome variable of interest. We're also going to be able to identify the explanatory variable of interest. Okay. However, in addition to the observed data, we're also going to draw unobserved vectors. What are those vectors? Well, one, these are unobserved vectors, so we don't really know what these factors are. These characteristics are. However, we can try to imagine, or we can try to kind of like, discuss the unobserved factors based on the context of the estimation. So what are these unobserved factors? Well, it could be unobserved motivation. It could be unobserved ability. If we talked about firm level, it could be unobserved culture. It could be unobserved entrepreneur skills of the owner of the business, and so on. So these are unobserved factors that could affect the outcomes, and something that is not readily observable in the data set. So we're going to kind of like divide the unobserved factors into 2 categories. Okay, so the first one is the component that doesn't change over time, and we're going to denote this as AI. So if you look at the textbook, some of the textbooks are going to use AI, some of them are going to use different notation, that's fine. However, just be mindful that when you see a panel data, usually you're going to specify that there is unobserved component that doesn't change over time. Again, it's an unobserved component that doesn't change over time. In this particular example, I'm going to denote this as A of I. Okay. Now, I'm going to call this unobserved effect or unobserved heterogeneity. Okay. Now, why do we call this unobserved heterogeneity? Because it varies by individual, but not by time. Okay. Since this is unobserved component that doesn't change over time, so it's going to be assumed to be fixed, or there could be changes, but not by much. And it's actually different from one individual to another individual. And so that's why we call it the unobserved heterogeneity. Okay. So at the individual level, you can think of this as ability, you can think of this as motivation, something that is innate and not subject to change. Okay. If you want to make it a bit more general, we can also refer to AI as unobserved attributes. There are also unobservable that changes across time, which is the U of I of t. So these are sometimes called shocks. Okay, we can also call them what's the idiosyncratic errors. They're specific to unit I, but vary over time. Okay, and at the same time, they also affect the outcome. So basically, this is hopefully exogenous shock that affect the outcome, and it's specific to that individual or that entity I, and it's different across time. Okay, so there are many cases of what the shock is. So for example, if we consider a panel data set of a student test score, so for example, for a particular individual during the end of the school year exam, just before, just a day or just maybe 2 days or 3 days or perhaps a week before the test score, the student got sick randomly. Again, this is randomly, and so we could, and we don't observe whether or not she was sick a day or probably a week before the exam. So this is an unobserved effect. And then since she was sick, it could also affect the performance of the exam, and then it could also affect the test score. But again, this is something that we do not observe as a researcher, and it only affects that individual, but it doesn't affect the other individual. Okay, so again, that's just an illustration, something that we don't necessarily observe in the data, but it could happen and then affect Y. So basically, again, we have two components. We have unobserved heterogeneity, and we also have the shocks or the idiosyncratic errors. So these two unobserved components, they both affect the outcome of interest, which is Y. Okay, so let's write the 2-period panel data. Okay, so we're going to have the outcome variable of entity I at period t, and then we're also going to have a time dummy. Okay, sometimes this is referred to as the time dummy, sometimes it's also referred to as the time fixed effect. Okay, so this is called the time dummy, or some people say that this is the time fixed effect. Okay, so d to t is going to be equal to 1 if t is equal to 2, and then 0 otherwise. Okay, so basically this is going to accommodate factors that affect Y, but is specific to the second time period relative to the first period. Okay, so we have what's called the composite error term here, and again we want to kind of like break down the composite error term into two. Okay, the first one is the unobserved heterogeneity, and the second one is the idiosyncratic error or the shocks. All right. Let's take a look at the composite error term. Okay, so again, we have two components. We have the unobserved component specific to that individual that do not change over time, or individual specific characteristic that do not change over time. Okay, we also have the idiosyncratic shocks, which is going to be useful for our discussion later on. So let's go through some of the assumptions needed given the structure of the composite error term. So basically, these assumptions are conditional on the regressors. However, we do not make it explicit here. And so first, we're going to have that the shocks conditional on the regressors is going to be equal to 0. And then the expected covariance between the shock of individual I and individual J conditional on observable is going to be 0. It means that the shock is specific to that individual and it doesn't affect the other individual. If we think that there is a shock or there are shocks that could affect not only one individual but also several individuals, then we may want to include that in the regression specification. So for example, it could be a region dummy, it could be a district dummy, it could be a provincial dummy. However, there is a note on using that in the analysis that we're going to do in several slides. And then there is no correlation between unobserved heterogeneity and then the shocks. So let's go back to the example of, the individual or the student who takes a test score. However, she or he was sick 2 days or perhaps a week before the test score, and then getting sick before the exam actually affects the exam performance. Okay. Now, whether or not a particular student got sick is not correlated with the unobserved characteristics. Okay, so for example, it's not more likely for students from poor families to get sick before the exam. Okay, and so if it happens not in a systematic manner, then we can assume that the shock is specific to that individual and it's independent of the unobserved heterogeneity or the unobserved characteristics. Okay, so whether or not a particular student got sick is really just a random event, conditional on the regressors, definitely. Okay, and then there is also another assumption that the shocks is also uncorrelated with the observable characteristics. That's another assumption that we're going to make. Now, for now, we're not going to make assumption on the correlation between the unobserved heterogeneity or unobserved component that do not change over time with the explanatory variable. Okay, so we're not going to make assumption on the relationship between unobserved ability, unobserved motivation with the observable characteristics of interest. Okay. So we're going to write the equation as the following. Again, we're going to regress the outcome variable of unit I at period t, and then we have a constant, and then we have a time dummy for the second period. Why can we include the time dummy for the first period? Again, so here the time category consists of year 1 and year 2, and if you have two categories, then at most you can have 2 minus 1 dummy. So either you have the first period dummy or the second period dummy. In this case, you want to use the second period dummy. And then you're going to have the explanatory variable. We're going to start with a simple model where we only have one explanatory variable of interest, but we can also extend the model to include more explanatory variables. And here we make it explicit that we have unobserved heterogeneity as well as the shocks. Okay. So the intercept in the first or the base period is beta 0, and that for the second period is going to be beta 0 plus delta 0. Okay. So it can be very important to allow changing intercepts to get a good estimate of a causal effect. Now, Note that xit does not change over time for any unit. Okay, so for example, if we observe gender, or for someone who completed the schooling variable doesn't change anymore. In a particularly short time period, the region in which the individual live, or the district in which individual live, doesn't really change by that much. Okay, so we can observe those kind of variables in the data set. Okay, so here in this case is gender and stuff like that. Now note that we will be limited in what we can learn in cases where we have variables that do not change over time. Okay, we'll see what's the consequences of having variables that do not change over time in a slide or two. Okay, so the first thing that we can do, given the data set and the structure of the panel data, is that what we can do is just use a pooled OLS analysis. Okay, and by using the pooled OLS analysis, we actually ignore, again, by just using the pooled OLS analysis, we actually ignore that there is a composite error term that consists of the unobserved heterogeneity and the shocks. Okay, and so since we cannot, and we actually ignore that there is a composite error term, so we just write it as just VIT. So we do not disentangle that in this VIT there is unobserved heterogeneity component, and there is that idiosyncratic or the shock component. Okay, so what we do is just we regress the outcome on a time dummy and then explanatory variable of interest. Okay, so if we apply OLS to the pool OLS estimation, we're going to get what's called the pool OLS estimator. Okay, again, we're going to look at, discuss an example of this in Stata in a few moments, but bear with me for now. So in this particular case, since we just regress Y on time dummy and then X, the statistical software doesn't acknowledge that it's actually a panel data set. Okay, so it's just a regression with a relatively long cross section. Okay, now there are few important issues arise with the pool OLS estimator. So the idea is that you have a panel data set, but you only take advantage, you actually do not take advantage by using the pool OLS estimator. So we need to identify another method to take full advantage of the panel data structure. But before we have that discussion, we're going to first discuss the issues of the application of pooled cross-section on panel data. So you're applying a simpler method for a richer data set, and you're going to get you're going to face consequences for that for sure. So we're going to discuss the first issue, which is it's a serious issue, but not as serious as the second issue. Okay, so let's start with the first. Now, suppose that we assume random sampling across I, which is very important in the assumption of multiple linear regression. We cannot reasonably assume that the observations for I across the first two periods are independent. Okay, now suppose that you take the composite error term for the first period, okay, and for the second period. And for each period, you're going to disentangle between the unobserved heterogeneity and then the shock. Now, as you can see, in both time periods, there is a common denominator, which is the unobserved heterogeneity. And what is going to be the consequence of this? Well, the main consequence is that now the shock in the composite error term in the first period is correlated with the unobserved or the composite error term in the second period due to the unobserved heterogeneity. So basically, the correlation of the composite error terms across time is going to cause the usual OLS standard errors to be invalid. Okay. And using heteroscedasticity robust standard errors does not really solve the problem. Okay, we're going to see a little bit of this in Stata. So it's a problem of serial correlation or cluster correlation because it's correlated within the unit I. So the unit I could be individual, it could be firms, and so on and so forth. Now, there's going to be a solution for this, which is called the cluster robust standard errors. And it's actually very, very simple to implement in statistical software nowadays. We're going to provide you with that example later on. Okay. All right. So that's the first issue. And as I said, the first issue is not as serious as the second issue. Okay. So we're going to talk about the second issue. Again, just to recall, the first issue is correlation of the composite error term across periods for a particular unit. Again, it happens for every unit in the panel data set. A more serious issue is that the consistency or the unbiasedness of the OLS. Okay, so basically, inconsistency or unbiasedness requires that the explanatory variables and the composite error term are not correlated. However, since the composite error term includes not only the shocks, again, we assume in previous slides that the shock is uncorrelated with the explanatory variable of interest, but we do not make any assumption on the relationship between the unobserved heterogeneity and the observable characteristics. Now, ideally, we're going to assume that there is no correlation between the unobserved heterogeneity, like ability, motivation, culture, and stuff like that, with the explanatory variable of interest, which is very unlikely. And then we're going to assume that the explanatory variables of interest is uncorrelated with the shocks. I think that's an assumption that we established in previous slides. Okay, so let's assume that this is an okay assumption. Okay, however, the first might be violated if xt is determined based on systematic difference of units. Okay, so for example, if YT is wage and then years of education can depend not only on one's unobserved ability or motivation, okay, that is captured by the unobserved heterogeneity component, but not on the contemporaneous shocks to wage, which is in the shocks. Okay, so when we violate the first assumption discussed in the previous slide, so we're gonna get what's called the heterogeneity bias. Okay, so it's a bias due to the fact that individuals are heterogeneous, and the heterogeneity is correlated with the explanatory variable of interest. Okay, so for example, more able or more motivated individuals are more likely to obtain higher education, and at the same time, they also have higher wages. So it's going to be quite difficult to disentangle whether this is the effect of the education or it's the effect of the education plus an unobserved ability or unobserved motivation. And so the bias is going to be referred to as the heterogeneity bias. Now, if the explanatory variable changes over time, at least for some unit in the population, there is a solution to mitigate or to eliminate the heterogeneity bias. What's the solution? The solution is by differencing away the unobserved heterogeneity. How can we do that? That's going to be the discussion in the next few slides. Okay. So the solution is going to be referred to as the first difference estimation. Okay. So to remove the source of a bias in a pooled OLS, what we can do is that we're going to write the time periods in reverse order. So we're going to start first with the second period and then the first period. So in the second period, notice that the d of 2t is going to be equal to 1. And so if it's 1, then you have the delta 0. And then you have the explanatory variable in the second period. You have the unobservability, and then you have the shocks. Okay. And in the first period, as you can see, the time dummy is going to be equal to 0. So you're basically just left with the beta 0. Now, what we can do is that we're going to take the first difference of this. We're going to take the first difference of this two periods. Okay. So if you take the first difference, we're going to get the outcome in the second period minus the outcome in the first period. And then since the beta 0 is eliminated, you're just left with delta 0. And then you have beta 1, and then you have the changes in the explanatory variable of interest across time. And then you also have the delta shocks. Okay. Now, what's interesting is that now you actually eliminate the unobserved heterogeneity. It seems very simple, and it seems that it doesn't have anything, it doesn't do anything special in just, eliminate the AI. However, when you enter into the estimation of this model, regressing using pool OLS and first difference would lead a very different estimates of the beta 1 coefficient. Another thing to note is that after the transformation or after the first differencing, there is not going to be any difference in the interpretation of beta 1. It's still going to be, the interpretation is still going to be consistent. So it's the change in the value of the outcome is the change in the value of the outcome is going to be beta 1 for every change in unit, for every 1 unit change in X. Okay, so that's going to be the interpretation. Okay, so let's define delta Y as the change in the outcome variable between the second and the first period. Okay, and then similarly, delta X is going to be the change in the explanatory variable in the second period minus the first period. Okay, we can also write the delta as C or the change, so it doesn't really matter. Okay, so again, we're still interested in beta 1. Okay, and then we have obtained an estimating equation by taking changes or differences. Again, we care about beta 1, and changing the estimation strategy doesn't really change the meaning of beta 1. It's still going to reflect the marginal effect of 1 unit change in X on Y. All right. So after the first differencing, notice that the intercept of the difference equation is actually the change in the intercept over time. Okay, so although it seems simple, the constant in this particular case, it's actually interesting to study the change. Okay, what's powerful about the first differencing method is that it eliminates the unobserved effect AI. Okay, we again in the previous minutes I said that it seems simple. However, a simple change can be quite powerful for isolating the causal effects. Okay, so if delta X is 0 for all I, or even if delta X is the same non-zero constant, the strategy doesn't really work. Okay, so it means that if X doesn't changes over time, then the first difference in strategy doesn't really work. So we need to identify the effect of a particular variable that changes on the outcome variable of interest. So X here needs to change. And again, later on, we can include some more explanatory variables to include in the data set. So we can use the simple OLS to estimate the change in Y on the change in X. This is also called the first difference estimator. With more than 2 time periods, other orders of differencing are actually possible. Hence, we want to name this particular strategy as first differencing instead of second order differencing. Okay, and the result is going to be first different estimator. All right, so let's take a look of an example. It's actually a very interesting example, and I'm going to provide you with an illustration that ignoring the rich panel data set and just use a pool OLS is going to provide you with a bias estimate of the effect of a particular variable. Okay. Now, in this particular case, we're going to identify the effect of unemployment rate on crime rate. So before we discuss any further, let's have 30 seconds to think about what would be the effect of unemployment on crime rate. Would higher unemployment rate increases crime rate, or would higher unemployment rate decreases crime rate? Well, it's actually more intuitive to hypothesize that higher unemployment rate is actually going to lead to higher crime rate. Okay, but we never know until we actually do the estimation. So let's do the estimation using the crime to data, and we're going to go to Stata now to identify that. Okay, so let's open up the data set. We're actually interested in the crime2 data set. Okay, let's take a look at the variables in the data set. Okay, so we have a lot of variables. We have the population, we have the crimes, we have the unemployment, we have the officers, the number of per capita income. We also have some dummy variables to indicate where the city is located. We have the year, which is year 82 and 87. So be careful here. It's not 1982 and 1987. It's actually just 82 and 87. So that's something that you need to be aware of. And this is the area of the land, which doesn't change over time. So this is kind of like the discussion that we had earlier. This is a variable that doesn't change over time. And then we have a time dummy for the second period, population density, crime rate, officers per square mile, law expenditure per capita, police per 1,000 people. So what we're interested in here is actually the crime rate and then the unemployment rate. Okay, my apology. So again, we're interested in the crime rate, crimes per 1,000 people, as well as unemployment rate. Okay. So the first thing that we're going to do is we're going to regress the pool cross-section model, okay, or the unobserved effects model. Okay, so here we don't acknowledge that there is unobserved heterogeneity. Okay, so let's see what's going to happen. Okay, so we have a crime rate. And then we have a time dummy for the second period. Second period in this case is 1987. And then we have the unemployment rate. Okay. Now we can definitely use the robust standard error. Okay, to identify general form of heteroscedasticity in the data set. Okay. And then we do a regression. So as you can see here, the estimated coefficient for unemployment is positive. Okay, so a higher unemployment is correlated with a higher crime rate. However, the effect is not precisely estimated. Okay, in fact, it's not statistically different to 0. Okay, now one of the issue of using the pooled OLS estimation is that we ignore the fact that the composite error terms are actually correlated across year. And we discussed in the slide that there is actually a solution for that, which is the cluster robust standard error. Okay, so we can go through that and then identify what can we do with it. But before that, we need to use an identifier for the cluster. Okay, Now, in this case, the cluster is the CDID. So what I'm going to do here is I'm going to use the eigen function to create the CDID by actually taking advantage of the area variable. So the area variable doesn't change over time, and it's specific to that particular CD. Okay, so we can identify the CDID. Now I'm going to redo the pooled OLS estimation of crime rate on second period dummy unemployment. Now, instead of using robust standard error, I'm going to use cluster robust standard error. Okay, so I'm going to use the VCE, and then I'm going to use the CDID as the cluster. Okay, so I'm going to write cluster and then CDID. Okay, so let's run the regression. So as you can see, after I adjust for the standard error, the robust standard error from the first regression using just general form of heteroscedasticity is actually different with the second period standard error. In particular, this estimated standard error using the cluster robust standard error is higher. So this is actually a typical observation when you conduct a panel data estimation and you do not control for the possibility that the unobserved error terms are correlated across time, then you will get underestimated standard error. And after you take into account the fact that the composite error terms or the shocks could be correlated across time, then your estimated standard error is going to be higher than in a regression that does not acknowledge the correlation. Okay, so it's going to be quite severe in some cases, the consequence, because having an underestimated standard error is going to lead to a higher probability of type 1 error. So that's something that you need to be mindful of. Okay. All right. So before I go further in terms of using the data set, since we have a panel data, we can actually now declare that it's a panel data so that Stata now knows I'm dealing with a panel data set. Okay, here we're just dealing with a pool cross section. Stata doesn't know that we actually have panel data. So by using the CDID and then the year, okay, we're going to tell Stata that, hey, let's start acknowledging that this is a panel data. Note that the data is between 82 and 87, so we need to identify that the difference in the year is 5 years in this case. Okay, so recall that the first difference model is just a regression of the change in the crime rate and the change in unemployment. So in Stata, what you can do is you're going to use the D dot crime rate on the D dot unemployment. Okay, and then in this case, you just have to use the robust standard error. You don't have to use the cluster robust standard error. Why? Because by differencing, you only have one unit of observation for each unit. Okay, and then I'm going to run the model. Now let's take a look at the regression without the first differencing method. So without the first differencing method, the expected or the estimated coefficient of unemployment is positive, but it's not statistically significant. Okay, and let's take a look at the estimated coefficient. In this particular case, the estimated effect of unemployment is way higher after you use the first difference estimation strategy. Okay, so in this particular case, a change in unemployment by a unit, which is usually by a 1 percentage point, is going to increase crime rate per thousand by about 2.2 or 2.2 crime per thousand, which is in this case economically significant. And then it's also statistically significant because the p-value is actually lower than 1% significance level. Okay, so this is basically the result of the regression when you're using first difference. Now, again, you can observe that it's very a simple change can yield or lead to a very significant change in the estimated coefficient. So you need to be mindful that this little change can actually mean a lot of things. Okay. All right. So the next question is, can we include more explanatory variables? The answer is yes. Okay. So what I'm going to do here, I'm going to include some more explanatory variables. Again, why do we need to include some more explanatory variables? We include more explanatory variables so that factors that affect y that would be otherwise in the unobservable or the composite error term will now be in the model, so that you reduce the possibility of getting a bias estimate of the unemployment effect. So what I'm going to do is I'm going to do a regression on the change of crime rate, okay, and the change of unemployment and all other explanatory variables. Now it's going to be quite tedious to write d dot for every variable. So what I'm going to do is I'm just going to write one d dot, but I'm going to apply this for all the variables in the data set. Okay. Okay, I can use the robust standard error as well. All right. So again, by including control variables, you can actually now get a higher estimated coefficient. In the previous estimation, you just get 2.21. In this particular estimation, you get 2.7. So we can see that if you do not include the explanatory variables, the estimated effect of unemployment would be underestimated. Okay. And an interesting observation is that it's still statistically significant. So this is the discussion of first differencing method. Again, it's a very simple strategy. It's a very simple manipulation of the model. Okay, just by first differencing, we can eliminate the unobserved heterogeneity, and by just using a simple manipulation, you could get a starking difference in the result. So this is, again, another feature of the panel data that we want to take advantage of. And this reminds you back to the idea of the multiple linear regression assumptions, particularly the zero conditional mean. If we fail to accommodate the fact that the explanatory variable of interest in this particular case is unemployment, is actually correlated with the unobserved factor in general. In this case is the unobserved heterogeneity. You could actually get a bias estimate. It could be underestimated, it could be overestimated. Again, there is no general rule of thumb. It really depends on the context and then the model of interest. But again, having a bias estimate will not do a lot of good things to you. So you need to make sure that before you do any regression, you need to identify potential endogeneity in the model. Okay, so that's the discussion on the first discussion on Stata. Again, I'm going to go back to the discussion in the lecture note just to provide you that we talked about this in Stata, but I just want to reiterate that not only that we can use one explanatory variable, we can actually use multiple explanatory variables, and you can still use the first difference strategy. Again, you need to make sure that all the x's change over time. If you have variables that do not change over time, you don't have to include it in the regression. Even if you do, well, the statistical software is going to drop the variable for you. Okay, so we want to interpret beta j as in the original equation. What is the effect of changing xj by 1 unit on the outcome variable of interest, holding fixed the other explanatory variables and the unobserved heterogeneity? So it's ceteris paribus not only on the observed variable, but also on the unobserved heterogeneity, which is quite interesting. Okay, so all explanatory variables get difference, whether they're dummy variables, squares, interactions, and so on. So you can actually include more flexible specification in the model. It doesn't really matter because it's also going to get difference as well. Okay, so the FD equation is going to be the estimating equation. Okay, what does it mean to be the estimating equation? It's going to be the estimation for you to estimate the coefficient, but by differencing, it doesn't really change the meaning of that coefficient. So the interpretation is still the same as if you have the original model. Now, the next question that you can actually ask is, can we do first differencing with more than 2 years of data? So far, we only have 2 years of data, but can we do differencing with more than 2 years of data? Well, first differencing can be used with more than 2 years of panel data. So the answer is yes, but you have to be really careful to account for serial correlation. Okay. Why? As we will see, now since we have more than 2 years of data, even though we eliminate the unobserved heterogeneity A of I, we do not eliminate the shocks. Okay, and the change in shocks can actually be correlated across time periods. And if it's correlated across time periods and we fail to account for that, then as we discussed earlier, there is a higher probability that you underestimate your standard error. And if you underestimate your standard error, then it may lead to a higher probability of type 1 error. So basically rejecting the true null hypothesis. In other words, you claim that a particular variable is statistically significant, although in reality it doesn't, it's not significant. Okay, so we should also include a full set of time dummies for more convincing analysis. So why do we want to include time dummy? We want to include time dummies or time fixed effects in the estimating equation because we want to try to accommodate changes that occur over time and is systematic, affecting all units in the equation. Again, we want to use the time fixed effects to accommodate aggregate changes that affect every unit in the data set. Okay, and it's unobserved. So that's the reason why we want to include time dummies. Okay, so suppose that we have t time periods. It could be 3 periods, 4, 5, 6, 7 periods, depending on the data that you have. So we can do the first differencing strategy, although later on you'll learn that it's actually not an optimal strategy if you have more than 2 periods and use first difference. But for now, let's stick with the first difference estimation, and then you can learn in the microeconometrics. So again, the model contains the unobserved heterogeneity as well as the idiosyncratic error. But again, we have more than 2 period in the data set. So as you can see, you have the time dummy for the second periods, third periods, fourth period until the capital T periods. Since we have T time periods, we can only have T minus 1 time periods, and then we eliminate the first year dummy out of the equation. Okay, just a little reminder of the dummy variable discussion. Okay, so when we do a difference, we're going to lose the first time period as before, but we are left with a panel data that we start with T equals to 3 and so on. So the first difference comes from observation at T minus the observation at T minus 1. So the difference between the current information and the previous time period information. So basically you have delta y for T equals to 2, and then you have delta y, which is for T equals to 3. So delta y for T equals to 3 means it's y3 minus y2, okay? And then delta y at T equals to 4 is going to be y4 minus y3, okay? And you also have a change in the dummy variables. Okay. We should also include that in the regression, and then we also have the um, change in the explanatory variable of interest. Okay. All right. So that's going to be the idea for the regression. Now let's go to this data, and I'll provide you with a simple example on how to use this given the data set. Okay. So for this discussion, I'm going to provide you with an example using the easy unemployment. This is a study by Papke that identified the effect of enterprise zone on the unemployment claims. Okay, they want to know whether or not the establishment of the enterprise zone reduces unemployment. Okay, so what are the data consist of? You have the unemployment claims as well as the enterprise zone. This is what we're interested in. Okay. Now, the first thing that we want to do, we want to declare the panel data set to data. So that's data acknowledges you're working with panel data, not just a simple pool cross section. Okay. And then in this particular case, we just have 1 year of data. And so we have 1 unit observation, one changes. Well, the time difference is 1 unit every year. Now, recall in the earlier discussion, we can have a strongly balanced panel data set. We can have unbalanced data set. And as we said, since this is a data at the aggregate level, at the city level, you're more likely to have a balanced data set. In other cases, if you have a individual or if you have household level data or firm level data, this may not be the case. So you're more likely to observe unobserved unbalanced panel data. Okay. So now data actually acknowledges that you're working with panel data, but before we do any estimation using the first difference strategy, I'm going to regress it using pooled data. So it's going to be the change in the unemployment claims at the that is log transform and then enterprise zone. And I'm going to use time dummies. Okay. So since there are many variables and then year is a categorical variable, I'm going to note to data, hey, year is a categorical variable. And then you have the robust standard error. Okay. So let's run the regression. So the regression estimated that the enterprise zone reduces the unemployment claims. However, it's not precisely estimated. In other words, it's actually not that different to zero. It's not statistically significant. Okay. And so, we'll try to get, do the estimation. But what we can do is we can also do the same regression. But what we can do is to try to accommodate the fact that the unobserved covariate are observable, are correlated across time. We're going to use the cluster robust standard error. Okay. Now take a look at the estimated standard error. In the regression with just the general heteroscedasticity robust standard error, the estimated standard error for enterprise zone is 0.1139. Now it doubles twice. So it doubled. So the estimated robust standard error doubles after you identify the fact that they're actually correlated across time. So be very mindful that if you have panel data, the error terms or the shocks can be correlated across time, and so you better want to accommodate that. Just one particular important note is that here we're working with a very small cluster. So ideally, we want to work with 100 clusters. Some people mentioned that working with 50 clusters is okay, but using the cluster robust standard error is actually more. It's actually more ideal if you have at least 100 cluster. Okay, but for the sake of illustration, I'm going to use the cluster robust standard error so that you'll be able to know that by not acknowledging the potential correlation of the shocks, you can get underestimated effect. Okay. Now let's do the first differencing method. So basically it's the log of the unemployment claims and then the easy, and then I'm going to include the dummies. Okay. And then I can use the robust, or I can use the VCE cluster and then CD. Okay. So two observations. Okay. So the first observation is that the estimated coefficient in absolute term is now larger. In other words, the enterprise zone effect is now higher if you use the first differencing strategy. Okay. So in particular, the establishment of the enterprise zone reduces the unemployment claims by about 18%. Recall that it's actually log of unemployment claims. And so you have to multiply the estimated coefficient by 100. Okay. So the establishment of the enterprise zones reduces the unemployment claims by about 18%, which is sizable effect compared to the previous estimated of 3.8%, which is not statistically significant. So what does it tell you? It tells you that, again, by just simply a simple manipulation to eliminate the unobserved heterogeneity is actually very, very powerful in obtaining the effect, or the true effect, or close to the true effect of the particular variable. In this case, is the intervention of enterprise zone. So what's the story or the morale behind this? The morale behind this is that regression analysis is not just about collecting variables and then regressing the control variables on the outcome variables, but you need to design a specification such that you'll be able to identify the effect of a particular variable of interest X on the outcome variable, controlling for other explanatory variables as well. Okay, so that's very important to note in this particular setting. All right, so I'm going to go back to our discussion on the note, and I'm going to go through some of the conclusions of the lecture this time. Okay, so there are key advantages of first inferencing panel data. So the first one is that it allows us to eliminate a time constant unobserved effect. So eliminating a time constant unobserved effect allows identification of causal effects. Okay. However, there are challenges in using the first differencing panel data. Again, the method is useless unless the explanatory variables vary over time. Okay. If it doesn't vary over time, Stata or other statistical software will acknowledge that. It's going to drop it right away. Okay, but just be mindful that it needs to vary over time. Okay. Now there are going to be issues when the key explanatory variable do not change over time. Okay, so if you do not observe much variation in X, then several things could happen, right? If you recall the discussion in previous chapters. The first one is that it could basically violate the third OLS assumption that the X variable needs to vary. That's one. The second issue is that the estimated standard error will be relatively large because the total variation in X is actually quite low. Okay, that's another issue. So you won't be able to detect an effect even if there is one. So another issue is that first difference estimation can be subject to serious biases, particularly if the strict exogeneity assumption is violated. So the strict exogeneity assumption is that there is no correlation between the explanatory variable of interest and other unobserved component. So the first difference strategy relies on the assumption that the only unobserved factor that could be correlated with the explanatory variable of interest is the unobserved heterogeneity, so that we do the first differencing to eliminate for the unobserved heterogeneity. Now, having more time periods generally does not reduce the inconsistency in the first difference estimator when the regressors are not strictly exogenous. And FD estimator can be worse than pooled OLS if one or more of the explanatory variables is subject to measurement error, and differencing a poorly measured regressor reduces its variation relative to its correlation with the difference error caused by the classical measurement error, and this will result in a bias. So first differencing strategy is actually not immune to the issue of measurement error. In fact, it will lead you to a bias if you have a high measurement error. Again, we would never know whether or not there is a measurement error in the variable that we're interested in, but it's always be good to contemplate before using that variable to check off whether or not there is an issue of measurement error, whether the zero conditional mean or the exogeneity assumption is fulfilled, and then the structure of the unobserved variable that could allow you to estimate a better standard error. Okay, so that's the discussion of panel data. It's actually the introduction of panel data. And again, if you're interested in panel data, you can go through it in microeconometrics course, in which you will actually learn advanced methods such as random effects, as well as the fixed effects. So very interesting discussions, but you'll have to wait for the microeconometrics course. All right. Thank you so much, everyone, for your attention. I hope that you'll have a exciting and good week. I'll see you in the next course. Thank you. Bye-bye.